Hello. In the previous video, we studied iterated integrals, and we use iterated integrals to solve the area problem in calculus 1. Today, we study double integrals, and we learn how to use such integrals to find volume of a solid region. Right? Before that, I would like to remind you the main idea how to solve the area problem in calculus 1. So look at this picture. We have function y equal to f of x, which is greater than or equal to 0 on some interval a and b. And we want to find the area of the region bounded by the graph of the function, the x-axis, the x equal to a and x equal to b. Remember, in calculus 1, we need to do some partition, right? That is the first step. So I have to divide the interval a and b into subintervals. Let's say subintervals of the same width, okay? And all of them have the length delta x. This is x0, this is x1, x2, and so on, and here is xn, okay? And then I will write the Riemann sum. The Riemann sum looks like this. Rn equal to sum from 1 to n. Here you have xi star and then delta x. Xi star is some point from here, from xi and xi plus 1. So, you can pick arbitrary point from there. You might pick left end points, you might pick right end points. But I write in general xi star. And here I would like to mention, we divide the interval a and b into subintervals of the same width. So that's why we have delta x right here. Only one delta x. But if you don't want to do that, it's okay. In general case, makes sense. You still have Riemann sum. And if you consider the limit of the Riemann sum when n approaches infinity, or in this situation, delta x approaches 0, this limit will give you the exact area of our region if the limit is x. Okay, so that is the area. And this limit is denoted by the definite integral from a to b of the function fx dx. So the main idea in this situation is you have to split the region into subregions. Okay, let me write in here. For example, you consider some subregion in here, and you pick xi star right here. For xi star, you have f of xi star. And then you approximate the area of this subregion by the area of this rectangle. Of course, each time when you approximate, you have some error, right? You do that for each interval, right? And then you sum them up. You get the Riemann sum. And then when you consider the limit, the error will go to 0. And that's why you get the exact area of the region. Okay? Now let's consider the problem how to find volume of a solid region using the same idea. Okay? Let me explain that first, and then we'll write out in detail. Suppose now we have some function z equal to f of xy, and this function is greater than or equal to 0. Okay, that is greater than or equal to 0. And this function describes some surface in R3. The region R is the domain of this function. Okay, and we want to find the volume of a solid region bounded by the surface of this function when x, y are in R. Okay, so you consider R in here, and in this picture you will see, yeah, actually they suppose that x and y greater than or equal to 0. But that does not matter in general case. Make sense? That is just an example. So your region R look like this. Okay, look like this. And now you want to approximate R using rectangles. So that's what you see in this picture. They divide R into sub-R, sub-regions. And they don't use rectangles like we did in the previous example. They don't use like this, right? They break this into sub-rectangles. You see that? Okay? And then for each sub-rectangles, that will create some rectangular prism. That is a rectangular prism. How? They pick some point, arbitrary point. For example, this is rectangle, let's say AI. Okay? They pick some point xi, yi belongs to AI. So they can find the function value right here, that is f of xi, yi. They have the height of this rectangular prism. They have the area of AI because, you know, the area of AI is just delta AI equal to xi, yi. I have a mistake right here. Delta AI should be delta xi times delta yi, okay? They can find the volume of this rectangular prism, right? And then they've moved to the next rectangles, right? And they do the same step. So they have the following picture, right? For each rectangle AI, they have one rectangular prism right here. And then they calculate the volume of each rectangular prism. They sum them up. They get a Riemann sum. Make sense? They get a Riemann sum right here. Okay? This is the Riemann sum multiplied with the what? Multiplied with f of xi, yi. Because f of xi, yi are heights, right? Of each rectangular prism. So they get some Riemann sum, and then they will consider the limit of this Riemann sum. If the limit exists, that limit is the exact volume of our solid region. Make sense? That's how we can use the idea from calculus 1. Basically, if you have to solve the area problem, you break your intervals into sub-intervals right here, right? And then you write the Riemann sum for that. Make sense? If you have solid region and they ask you to find volume, so you break the solid region into sub-solid regions corresponding to rectangles in the domain R. And then you have some picture like this, right? And you write the Riemann sum for that, and you take the limit, okay? All right, so let's write the Riemann sum for the volume. But before that, I say we have R. Let's rewrite the function z equal to f of x. You have R in R2. This function is greater than or equal to 0. And let's say R2, not only that, xy greater than or equal to 0. Okay. And then you have to do some partition. You break R into rectangles AI. Okay. For each AI, you have area of AI, which is delta AI. Alright. And then from AI, you pick some point xi, yi. So for this point, you have the height of your rectangular prism. The height is f xi, yi. And then you can find the volume of a rectangular prism. That is the area of AI times the height, f of xi, yi. And then you sum them up, you get a Riemann sum. Okay, your Riemann sum looks like this. Rn equal to sum I from 1 to n, f of xi, yi, and then delta ai. Next, you do some limit process. You consider the limit of Rn, which is the limit of sum I from 1 to n, f of xi, yi, and then delta ai. Here's the thing. So you may do a limit when n approaches infinity, right? In case if all delta ai are the same, right? Or in general, you may write each time you have maximum, for each partition you have maximum of delta, right? And this delta, the maximum area, just approaches 0. Makes sense? And then if this limit is x, this gives you the exact volume of the solid region. And this is denoted by the double integral on the region R of the function f y dA. Similar to the case of different integrals of function of one variable. If you have delta x in here, you go to dx, right? But here you have delta ai, you go to di, where a is the area. Make sense? So that's how we can define a definite integral, and how we can use definite integral to find the volume of a solid region. Okay? As definite integrals are function of one variable, double integrals also have some properties. Let's talk about this and then we move to detailed examples. The first one. When you multiply a function with some constant, you can take that out of the integral. Okay? That is from the definition. The second one, double integral of f xy plus minus g xy. That is double integral of f, I write in short here dA plus double integral of g dA. Okay. The third one, double integral of the function fy dA is greater than or equal to 0 if the function is always greater than or equal to 0. Because in this case, this double integral gives you the volume of solid region bounded by the surface of the function z equal to fxy, right? And volume, of course, would be greater than or equal to 0. The next property, if you have fxy greater than or equal to gxy on R, then the double integral of f dA would be greater than or equal to double integral of g dA. That is also natural. So you say, yeah, if f is greater than or equal to g, then the surface described by the function f is higher than the surface described by the function g. So the solid region for f would be bigger than the solid region described by g. And actually the solid region described by g is included in the solid region described by f. That's why the volume of the first one would be greater than the volume of the second one. Okay, and then if you break R into R1 and R2, right, such that R1 and R2 don't intersect with each other. Let's say that. I mean, in the sense that they may intersect, but by some line, right? So they don't have common area. Let's say that. Okay. Then we have integral of f on R equal to integral of f on R1 plus integral of f on R2. Those properties are very natural. Okay. Let's consider the following example, and we'll see how the Riemann sum works. We have function f of xy equal to 1 minus 1/2 x squared minus 1/2 y squared. This is the equation of the paraboloid. And we have some region R, which is square on the x or y plane. X is between 0, 1 and y is between 0, 1. They ask us to approximate the volume of a solid region lying between the paraboloid and the square region R. Need to use the partition made up of squares whose sides have a length of 1/4. The partition looks like this. Here's R. That is 1, that is 1/2, that is 0, that is 1/4, that is 3/4, that is 1/4, that is 1/2. I have more than this, 3/4, and then 1 right here. Okay, so this is the square. This is R. We need to make some partition on the R. They ask us to use squares. So we have the following partition. Okay, so we have 16 squares. Right? So this is my AI. Basically, I already have AI, and the area of AI equal to 1/4 times 1/4, which is 1/16. So all areas are the same. That is good. All right. The problem is now we need to pick arbitrary point. Let's say that is xi, yi. Makes sense? And then from there we can write the Riemann sum Rn equal to sum r from 1 to n f of xi, yi in here, and then delta ai. We just need to plug xi, yi into the function. So the function is what? Is 1 minus 1/2 xi squared minus 1/2 yi squared times 1/16. So you can write, 1/16 sum r from 1 to n, 1 minus 1/2 xi squared minus 1/2 yi squared. In this case, n is 16, so I would write right here R16. Okay, this is R16, and n is 16. Make sense? Okay, now let's just work out for some xi, ii. Okay, because in calculus 1, when we did that, we can use right endpoints or left endpoints or midpoints, whatever we want. Let's do similar things for this situation. Let's choose right endpoints all the time. Okay, so if I choose right endpoints all the time, for x, I would have the following points: 1/4, 1/2, 3/4, and 1. It's what we have in here, the partition, right? 0, 1 for the x. And for the y, I will have the following point: this, and this. Makes sense? So if I want to choose right endpoints all the time, I need to consider x, which is 1/4, 1/2, 3/4, and 1. And the y is 1/4, 1/2, 3/4, and 1. That makes sense? And then I will consider the Cartesian product xy, which is equal to xy such that x belongs to x and y belongs to y. And then you will run the Riemann sum over the Cartesian product x times y. You know, we have 16 elements in this set, in this Cartesian product. Make sense? Just let me list some of them, okay? That is 1/4, and then you have 1/4, 1/4, 1/4 with 1/2, 1/4 with 3/4, and then 1/4 with 1. Where are they on the graph? If x is 1/4 right here, 1/4, 1/4 is right here. Make sense? That is the first point. That is the first point. 1/4, 1/2, second point. 1/4, 3/4, and then 1/4, 1. So basically, you have 4 points right here. You see that? And then after that, you move to 1/2, right? And then you make points between 1/2 and 1/4, 1/2, 3/4, and 1. You have the following points on the graph. And so all the points right here, you see? So basically, if you use right endpoints all the time, you have that. And then the last step is just plug all these points in the Cartesian product of x and y into the Riemann sum to find the estimate of the volume. I can write like this: R16 is equal to 1/16. Okay, the first is 1 minus 1/2, 1/4 square minus 1/2, 1/4 square. That is the first term for the first point right here. Make sense? And then take 1 minus 1/2, 1/4 square minus 1/2, 1/2 square. So that is for the second point right here. And so on. And then you simplify it, you get the estimate of the volume of our solid region. In this example, we will find the volume of solid region bounded by the plane z equal to 2 minus x minus 2y and the 3 coordinate planes. Here's the picture. So you have x or y and z, 0, x, y, and z. You can consider points right here. You just put y and z equal to 0. So the x is equal to 2. Okay. And then another point on the y axis, which is 0, 1, and 0. It's easy. You put x and z equal to 0 and plug into the equation of the plane. You get y equal to 1. And finally, the z is also equal to 2 when x and y equal to 0. So you have 3 points in here. And then you just connect them. You get some region like this. Makes sense? And they ask us to find the volume of this region. Okay, so how to do that? That is the plane z equal to 2 minus x minus 2y. So if we consider double integrals, right, and use double integral to solve this problem, we would have the following one. The volume is equal to double integral on R, where R is triangle on the x or y plane of the function f of x and y dA. Make sense? But what is dA in this situation? So we need to do partition and then make the Riemann sum and then integrate that. It's a very long way. On this picture, if I consider some cut, so I fix some x right here, okay? I fix some x right here, and then I consider a cut like this, a cut like this. So basically, what is that? This line is parallel to the y-axis, and this line is parallel to the z-axis. Make sense? So we can find coordinate of this point and this point. How? The coordinate of this point is equal to z equal to 2 minus x, because in this case y is equal to 0, and from the equation of the plane we have z equal to 2 minus x. For the second point right here, that is just y equal to 2 minus x over 2. Why? Because you plug z equal to 0 into the equation of the plane, and so for the y. Make sense? All right, so if you fix some x in here, you can find coordinates of this point and this point easily. Okay, so you have some triangle which is parallel to the y-OZ plane. And then you can find the area of this triangle. Make sense? You can find the area of this triangle. Let's say the triangle is A. So you can find the area. And of course, this depends on x. So the area AX is equal to the y coordinate times 1/2 times z coordinate, right? And that is 1/2. The y is 2 minus x over 2 times 2 minus x. So you have the area of this guy. And then how to find the volume? In order to find the volume, I just move this triangle along the x-axis. So I move along the x-axis, and x goes from 0 to 2. So basically, using this idea, we can find the volume equal to integral from 0 to 2 ax dx. Make sense? And we already have ax. We just plug everything into this integral. That is 1/2 times 2 minus x squared over 2 dx. And that is 1/4, 0 to 2, 2 minus x squared dx. We use the power rule. That is negative 1/4, 2 minus x over 3 over 3. Evaluated from 0 to 2. So at the end you get 2/3. And that is the volume of our solid region. Make sense? Of course, you might choose another one. You don't want to fix x. And now if you want to fix y, how that works? If you want to fix y, you see the following. I will fix y right here. And I consider some cut. Okay. So I have another triangle in here. Makes sense? And then I need to find the area of this triangle. And then I evaluate integral with respect to the y on the interval from 0 to 1. Make sense? Okay, let's go out in that direction. So if I fix y right here. I need to find the x and y and the z coordinate. In order to find the x coordinate of this point, I just put z equal to 0. Okay, for this point, I put z equal to 0 and solve the equation of the plane for the x. For that, I get x equal to 2 minus 2y. And I can find, the z coordinate of this point. I have z equal to 2 minus 2y again, right? And then I can find the area of that triangle, of this triangle. The area is equal to 1/2 x times z, which is 1/2, 2 minus 2y squared And then I can find the volume equal to integral from 0 to 1, because now we integrate with respect to the y. 1/2 2 minus 2y squared dy. And I bet you get exactly the same number. Makes sense to us. Now, let's compare this with the iterated integrals we learned in the previous video. It seems like when we consider cuts, you would think, yeah, we fix x or we fix y. Do you remember that? When we write integrals in different orders, dy, dx, and dx, dy. Let me remind you about that. When you want to rewrite the integral, iterated integral, dx, dy in here you have some function x and y, and you want to change this into dy dx, means you want to change the order of integration in iterated integrals. So basically, each time when you do that, you need to change the integration limits in here, and in here, in here, and in here, in here, and in here. Make sense? So what happened in our situation? We write the volume that is double integral on R, right? F of x, y, dA. And now, how to attack dA? Remember that the area of each AI is equal to delta xi and times delta yi. Right? So when you go from this notation to integrals, that would go from delta ai to dA, delta xi to dx, delta yi to dy. That means you may have hope to rewrite this integral in terms of iterated integral. Makes sense? But it really depends on how you use the order dx dy or dy dx. Make sense? If you want to rewrite this integral in the form of iterated integral, and you write in the order dx dy. Look at this, dx dy, right? So the y, you need to fix the y first. Makes sense? If you fix the y, you are in the second situation right here. Makes sense? If you fix the x, you are in the first situation right here. Right here. So how to see that? If you fix y, you will integrate with respect to the x first. And your function is still the same. Your function is what? It's 2 minus x minus 2y right here. Since you integrate with respect to the x, now you have to find x depending on y. That's what we are doing right here. You see that? And then you can see this picture. If you fix y, then the x will go from where to where? X will go from 0 to this point. Let me draw that separately, okay? So here's the triangle in x or y plane. That is 2 and this is 1, right? And we have triangle like this. So if you fix y, I fix some y right here. X will go from where? From 0 to this point. You see that? So we already found the point, the coordinate of this point on this example. That is 2 minus 2y. So I can find, yeah, that is 2 minus 2y. Then the integral inside of this is just equal to integral from 0 to 2 minus 2y, x 2 minus x minus 2y dx dy. And y will be from 0 to 1. Look at this, from 0 to 1. So you integrate the function with respect to the x first, okay? And then you integrate with respect to the y. So you get 2 integral from 0 to 1. I will compile 2 minus 2y, okay, together, because, you know, in this case, they are just constants. So that is x in here, and then minus x squared over 2. And this is evaluated from 0 to 2 minus 2y, and then dy. Make sense? And then I will plug 0 and 2 minus 2y into the function. At 0, the function is 0. At 2 minus 2y, I have the following one. 2 minus 2y times 2 minus 2y, and then minus 2 minus 2y squared over 2, and then dy. You simplify this, you get integral from 0 to 1, 2 minus 2y squared over 2 dy. That's what you got in here. Makes sense when you fix y. And in that case, you write the integral in the order dx dy. That means you integrate with respect to the x first, and then you integrate with respect to the y. Okay, so now how to write the double integral in terms of iterated integrals, right? But in the other order. Let's do that together. Now I want to rewrite the integral in this order. 2 minus x minus 2y dy dx. Okay, again I will make the triangle. That is my y, that is my x. Here is 1, here is 2. So I have this triangle. Now I fix x because, you know, I integrate the y first, right? In that situation, x is a constant. Makes sense? So I fix x. I fix 1x right here. Sorry. I fix 1x right here. Okay. I make some cut because I fix x. So from this picture, I will see, yeah, y will go from where to where? Y will go from 0 to this point. Makes sense? And so I need to find the coordinate of this point. Y equal to 2 minus x over 2. You put this equal to 0. Makes sense? And so for the y. And for this, for the very first situation, how to find 2 minus 2x? Again, you put the function equal to 0 and you solve for x. It's pretty easy. You see that? All right. So now I will have the following picture. The outside integral is for the x. X will go from where? From 0 to 2. And then for the inside, y will go from 0 to 2 minus x over 2. The function is still 2 minus x minus 2y. dy dx. You see that? So let's integrate this function, the inside function first. And then this equal to 0 to 2. We integrate with respect to the y. 2 minus x is constant, so I get 2 minus x times y in here minus y squared, because 2 already cancel out. Evaluated from 0 to 2 minus x over 2 dx. Inside I have 0 to 2. I plug 0 and 2 minus x over 2. At 0, again, the function is 0, right? At 2 minus x over 2, I get 2 minus x times 2 minus x over 2 minus 2 minus x squared over 4, right? Because we square dx. If I simplify that, I will get 0 to 2, 2 minus x squared over 4 dx. Let's compare with the first situation we have right here. Look at this. This example is really important in my opinion because we learn how to rewrite a double integral as iterated integrals. And we learn how to write integrals in different orders. Dx dy or dy dx. Makes sense? The key moment in this is the following two pictures. you need to consider different cuts. And for the first one, if you fix y, right? If you fix y, so you have to fix y like this. Makes sense? You make a horizontal line, and that horizontal line will intersect with this straight line at some point, and you need to find the coordinate of this guy. But the coordinate of this guy is easy. You know, you just put the whole function equal to 0 in here, and so for the x, you see that? And for the second case, when you want to write in the order dy dx, you fix x right here, and you need to find the y coordinate of this point. For that, you just put the whole function equal to 0, and you solve for the y. Make sense? So if you understand this picture, you can rewrite most of double integrals in the form of iterated integrals easily. Okay? Let's consider the following example. Find the volume of solid region bounded by the parabola z equal to 4 minus x squared minus 2y squared and the xy plane as shown in the picture. So you have the picture on your screen. The surface z equal to 4 minus x squared minus 2y squared right here, okay? And you need to find the volume of this solid region. All right, so we know that the volume is equal to definite integral on R of the function dA, right? Now we need to just rewrite in the form of iterated. But what is R in this situation? How to find R? They didn't give us, but they say, yeah, the R should be on xy plane, and that's, you know, that is some kind of intersection, right? Inside of the intersection between this parabola and xy plane. So in order to find that intersection, everything inside of the intersection between the parabola and the xy plane. Makes sense? So in order to find that, you just put z equal to 0, okay? So from the equation I have, that is 4 minus x squared minus 2y squared equal to 0. Or that is x squared minus plus 2y squared equal to 4. So you might think, yeah, that is an ellipse, right? That is an ellipse. In the xy plane, I have the following picture. X, Y. So you have ellipse right here, and somewhere right here. Okay? Somewhere right here, somewhere right here, and somewhere right here. It's not a good picture, but it's fine. We have an ellipse. Okay? And the region R is this. It's easy to find coordinates of this point, this point, this point, right? You just put x equal to 0. You can find y is negative square root of 2 and square root of 2 from the equation of the ellipse. And you put y equal to 0, you can find this is negative 2 and this is 2. The first case, I want to rewrite this integral in terms of what? In terms of integral on R, f of xy, dx, dy. Agree? So that means in this situation, we need to fix y, and then we need to find the interval of x. Make sense? Look at this picture. We fix y. We fix y, we make some horizontal line. That is y, we fix y. So how to find the interval of x? We can find the intersection of that line with the ellipse. We have 2 points right here, and we need to find this coordinate and this coordinate. And of course, according to this picture, x will go from x1 to x2. Make sense? All right, so I just need to solve the equation, right? For the x, if I fix y. So if I fix y, my x should be equal to 4 minus 2y squared. And from here, I can see x equal to plus minus square root of 4 minus 2y squared. So that means x will go from where? Go from negative square root of 4 minus 2y squared and to 4 minus 2y squared. After this, I can rewrite my integral. The integral looks like integral from negative 4 minus 2y squared to square root of 4 minus 2y squared. The function is the same, that is 4 minus x squared minus 2y squared. Here should be dx, right? And outside is dy. But we still need to find the integration limits for the y. They are here. Because we fix y, right? Y go from negative square root of 2 to square root of 2. So that is one iterated integral. If we integrate in this order. Make sense? Okay, let's write the second one when we change the order, okay? Now I want to write in the order dy dx. The function is still 4 minus x squared minus 2y squared. So I need to find integration limits in here, and in here. For the x, everything is good because we know x will go from negative 2 to 2, right? Negative 2 to 2. Make sense? And now for the y, we fix x in this situation. If we fix x, I will make some line in here. Make sense? Because I fix x. I fix x right here. So I make some vertical line. And that vertical line will intersect with the ellipse at 2 points. I need to find the y coordinate of this point and this point. So this is y1, that is y2. I need to find y1 and y2. But that is easy again, right? So you just solve the equation of the ellipse with respect to the y. Make sense? So I will solve the equation of the ellipse with respect to the y. I have 2y squared equal to 4 minus x squared. And y squared equal to 4 minus x squared over 2. So y is equal to plus minus square root of 4 minus x squared over 2. That means y goes from negative square root of 4 minus x squared over 2 to square root of 4 minus x squared over 2. And now you just copy this and this into the integral. And you are done. Let me rewrite it. So the integral looks like integral from negative 2 to 2 from negative square root of 4 minus x squared over 2 to square root of 4 minus x squared over 2. Okay, the function is 4 minus x squared minus 2y squared dy dx. So you have two forms already. And now your job is to pick one of them, right? The first one is right here. This is the second one. So you can pick one of them to solve and to find the volume of this solid region. Let's pick the last one. Okay, let's pick this one. I need to integrate the function with respect to the y. Okay, so I have, that is negative 2 to 2 right here. Here I don't have integral anymore. I will find antiderivative right away. So I have 4 minus x squared times y, because 4 minus x squared is constant in this case, right? We integrate with respect to the y, minus 2y cubed over 3, or this function evaluated from negative square root of 4 minus x squared over 2 to 4 minus x squared over 2 square root. And then dx. Okay, so when you plug these two integration limits into this function, you get the following one: negative 2 to 2, you have 4 minus x squared, and then square root of 4 minus x squared over 2, minus 2/3, 4 minus x squared over 2 square, and then cube, minus negative of the whole value right here, dx. Makes sense? So you have double, 2 times negative 2 to 2, and here you have 4 minus x squared, and square root of 4 minus x squared over square root of 2 minus 3, 2 over 3, and then 2 cubed. So I would write 2 square root of 2 right here, and then here I have 4 minus x squared cubed dx. We might simplify something in here. 2 with 2 will be cancelled out, right? So you have square of 2. So basically the coefficient right here, you know, this is equal to this part, right? The coefficient is 1 square root 2 minus 1/3 and square root 2. So basically that is what? That is 3 square root of 2 here, and then you have 2 square root of 2. So you get 2/3. No, not 2/3. You get 2 over square root of 2, right? So basically that is square root of 2 over 3. I can take that out, right? I can take that out. So basically the integral will be equal to 2 square root of 2 over 3 in here. Integral from negative 2 to 2, 4 minus x squared. I write 3 over 2 dx. Agree? So you see, you know, basically we can simplify more because you integrate x with, from negative 2 to 2, right? And your function is an even function. An even function in here. So basically if you want, you can simplify like this. That is 2 times 2 square root of 2 over 3 integral from 0 to 2. 4 minus x squared, 3 over 2 dx. Okay? Alright, so how to solve this integral? From calculus 2, you have different, you know, integrals involving trig functions. You have different forms like this. A squared minus x squared, x squared minus a squared plus x squared. Alright? So for this form, you would put x equal to sine of theta. Make sense? We are in this situation. So if I put x equal to sine of theta, I have the following one. In this case, a is 2, okay? No, 2 sine of theta. So I have 4, let's do that right here. X equal to 2 sine of theta. So I have dx equal to 2 cosine theta d theta, and 4 minus x squared equal to 4 minus 4 sine squared theta, which is 4 times 1 minus sine squared theta, and 1 minus sine squared is just cosine, right? Okay, and of course you need to change the integration limits too, right? So when x equal to 0, I can find theta is equal to 0. When x equal to 2, I can solve for theta. That is sine theta equal to 1, right? So you can solve that. Theta is equal to pi over 2. So basically, when you do changing the integration limits in here, your integral will be equal to 2, 4 times square root of 2 over 3. Integral from 0 to pi over 2. Okay, so inside you have 4 cosine squared theta square root cube. Dx is 2 cosine theta d theta. And then what is that? That is 4 times square root of 2 over 3 integral from 0 to pi over 2. When x go from 0 to pi over 2, sine, cosine are positive, right? And when you apply square root to cosine square, that is just cosine of theta. Make sense? So you have the following one. Cosine of theta cube times square root of 4 is 2. 2 cube is 8. Okay? And then 2 times cosine of theta d theta. So you have the following one. 4 square root of 2 over 3. 8 with 2 is 16. I write 16 in here. Okay? Integral from 0 to pi over 2 cosine 4 d theta. Again, how to solve this? Integral. You may use integration tables, but for such integral, you need to use double angle formula, right? You need to do the following way. So if I apply cosine 2 theta equal to 2 cosine square theta minus 1. From here I get cosine square theta equal to cosine 2 theta plus 1 over 2. And then here you have power 4, right? Basically you have cosine 2 4 equal to cosine of 2 theta plus 1 over 2 and square. So it's very long, makes sense? But you know, let's do that to the end. You have 4 square root of 2 over 3 integral from 0 to pi over 2, and then cosine of 2 theta plus 1 over 2 square d theta. And you have to open this square. You get 16. 4 square root of 2 over 3 integral from 0 to pi over 2. You have cosine square of 2 theta plus 2 times cosine of 2 theta plus 1 over 4 d theta. So you might simplify 4 with the 4 right here, okay? And that is 16 square root of 2 over 3 integral from 0 to pi over 2. And cosine square 2 theta plus 2 cosine 2 theta plus 1 d theta. For this, we are good. For this, we still need to use double angle formula. Okay? So by the double angle formula, I have cosine square 2 theta is equal to cosine 4 theta plus 1 over 2. Look at this. So I will write this integral as 16 square root of 2 over 3 from 0 to pi over 2 cosine 4 theta plus 1 over 2 d theta. Let's break this into integrals. 2 cosine 2 times cosine of 2 theta d theta plus integral from 0 to pi over 2 d theta. This is equal to pi over 2. This is equal to antiderivative of cosine is sine, right? So you have 2 times sine 2 theta over 2 evaluated from 0 to pi over 2. Okay? And for this integral, you might think, yeah, that is integral from 0 to pi over 2 cosine 4 theta over 2 plus 1/2 d theta. And that is equal to 0 to pi over 2, 1/2 right here, cosine 4 theta d theta plus 1/2, 0 to pi half d theta. And this is equal to pi over 4. This is equal to 1/2 times 1/4 sine of 4 theta evaluated from 0 to pi over 2. You see? And now, what is this? So you just plug pi over 2 and 0 into this, you get 0 right here, which is good. This is just pi over 4 overall. This integral is just pi over 4, right? So you compile everything, you get the following one. The answer is 16 square root of 2 over 3 times pi over 4 plus, so you plug pi over 2 and 0 into this, you also get 0. Perfect, plus pi over 2, which is equal to 16 square root of 2 over 3 times pi over 4 plus 2 pi over 4, and you simplify that, you get, on the top you get 3 pi over 4, right? This part. So you have 16 square root of 2 over 3 times 3 pi over 4. The answer is 3 with 3 will cancel out, 16 with the 4, so you get 4 square root of 2 pi. Wow, look at this. That's how we can find the volume of a solid region. It's a very long way, but you know, that's all we need to do. In the following example, I will show you how to rewrite a double integral in iterated form, okay? I will not solve that to the end, so you can see the detailed solutions in the textbook. Find the volume of the solid region bounded by the surface fxy equal to e to negative x squared and the planes z equal to 0, y equal to 0, y equal to x, and x equal to 1. Now we don't have any picture of that solid region, but we know exactly z, x, y 0, right? And y equal to x and x with the 1. So that means in this situation, y, x, and z greater than or equal to 0, which is good. So I just go ahead to make the region R, okay? So I need to make the region R because that is the most important one. X, O, and Y in here. Y equal to X. That is Y equal to X. X goes from 0 to 1. 0 to 1 right here. Okay. The region look like this. Okay. Okay, so we know the volume is equal to R fxy dA, and if you want to write in the form dx dy, you may have the following one. The function is e to negative x squared, or you want to write e to negative x squared dy dx. So basically we need to play with the integration limits. Make sense? All right, so for the first case, with the order dx dy, I fix y, right, and I need to find x. I fix y, I do the following one. I fix y right here. Okay, so here's the my intersection in here and in here. Basically, x should go from this point to this point. Makes sense? So 1 is already right here. We need to find the coordinate of this guy. But that is easy. You can find that easily because y equal to x. You see, the y is equal to x. So if this is y, this should be y. So I can find x go from y to 1, and y go from where to where? From 0 to 1. Make sense? Because you know, y is this. Y should go from 0 to this point, right? So that is 1 because y equal to x. All right, so next. You can write dy dx, right? So you fix x. Let me make another picture. Okay, it's more clear. So I fix x. Here's y equal to x. That is y. This is x. This is 1. This also 1, 0 right here. The region is right here. Now you fix x because you want to rewrite in the form dx dy. You fix x. I fix some x right here. This is my cut. I need to find this point, but this is also x, right? So if I fix x, the integral outside should be from 0 to 1 because we know this. The second one inside should go from where? From 0 to x. From 0 to x. Okay, so you might pick one of them and solve to find the volume of our solid region. If you look at the first integral, it's no way to solve this. I cannot find antiderivative of e to negative x squared, right? Of course, you can use series. You can expand this function as a power series and then integrate that and then sum them up again. But that is a very long way. In that situation, I pick the second one, right? Because if I integrate the function with respect to the y, this is nothing but the constant, right? The constant. So if that is constant, so it's easy to handle. So like in here, I have integral from 0 to 1, and you have e to negative x squared, x evaluated from where? From 0. Y evaluated from 0 to x dx. And that is what? That is e to negative x squared from 0 to 1. I have x dx. And we know how to solve such integral by put u equal to negative x squared. Make sense? All right, so I think we can finish our lecture right here. We still have a couple of examples in the textbook, but I very encourage you to do that. The most important is to rewrite a double integral in terms of iterated integral. And like this example, you have to pick one of them, right? Sometimes you cannot solve all. Sometimes you have to choose that. But anyway, we need to know how to rewrite a double integral in terms of iterated. That is the most important in this chapter. Don't forget about that. Thank you and see you in the next video.